welcome to Basics of Finite Element Analysis Part 2. Today is the 5th day of this week, and going forward we will be introducing a new topic, and which deals with how do we go around doing finite element analysis of problems which are governed by partial differential equations in 2 dimensions, and these differential equations could govern the processes where one single variable is involved or multiple variables are involved. But for starters, we will be doing 2-dimensional problems involving a single variable. So, with that, let us first lay out the overall nature of problems we will discuss in context of 2D problems with one variable. So, two-dimensional problems, right. So, first we will classify these problems. So, you can have these problems involving one variable, you can have problems involving 2 variables, or you can have even more, 2 or more. What would be the example of a one variable problem? Suppose I have a plate of this shape. So, if I look at this plate, so this is x and this is y, and this is the top view of the plate, and if I look at it from the side, then the plate is, it looks like this. So, this is top view and this is side view. This is my x direction and this is my z direction. And this is a plate, and let us say that this plate is insulated . Z, sorry. So, this is Z and this is X, Y. So, suppose I have this plate, and let us say part of this edge of the plate is insulated, and then I have natural convection in other parts of the plate, and in some part I am injecting some heat. So, I am heating from on a portion of the edge, the other part is open. So, it can have it is open, and this other edge is insulated, and if I am interested in finding the temperature at any point. So, here there is one single variable T, but it varies with respect to x and y. Okay. So, it is a 2-dimensional problem involving one single variable, which is T. Okay. So, this is a 2D problem with one variable. There could be other problem. Okay. I could have a similar plate where I am fixing one part of the edge, and the other and the other part, remaining part, I am just pulling it, and because of that pulling there will be displacements in the plate, and let us say those displacement in x and y directions are u and v respectively, then it will be a 2-dimensional problem involving 2 variables. Right. So, you can have a 2D problem with one variable, 2 variable, or n number of variables. So, these are 2 broad categories: 2D problems with one variable and 2D problems with 2 variables. And then these things can be reclassified into three types of problems. One is boundary value problem. Then you have initial value problem. And the third one is eigenvalue problem. Okay. So, we had described these three different type problems in part 1, but so this is abbreviated as BVP, this is IVP, this is EVP. So, in boundary value problem, we do not consider time effects. So, there could be a plate and whatever solutions we are getting, it is the steady state solution, it does not change with time, that is a boundary value problem. In initial value problem, time effects are also incorporated. So, suppose I have a plate and I just started heating it from a part of the edge, and then it takes maybe 10 minutes for the plate to reach a steady state temperature, but how is temperature changing with time will depend on the initial state of the plate also, and also the boundary conditions. So, those problems are initial value problems, and then in eigenvalue problems we calculate the eigenvalues of the system, and we do not in that case consider the role of initial conditions and also the role of force related boundary conditions. So, these are three categories of problems, and what we will be discussing as we go forward are 2D problems with one variable, BVP boundary value type, initial value type and eigenvalue type, all these three categories. We will now look at an equation, and this equation is called Poisson's equation. And it is an important equation because if we solve this particular equation, we can solve a very large number of different types of problems. So, this is written as minus, and there is this inverted triangle symbol known as gradient operator, and then I take a dot product. So, it is a vector operator. So, and then I take its dot product with k, a constant or a function of x and y, it could be either, times gradient of a variable. So, u is not displacement, it is a variable and it is a scalar variable, it does not change with direction, and that equals f. So, here k could be a function of x and y, u is certainly a function of x and y, and f could be a function of x and y, and then of course, so all these are scalars. So, they are not changing with direction. And the other thing is that the gradient operator is defined as del over del x plus unit vector in y direction, which is j, times del over del y. So, this Poisson's equation is having a lot of applications, very large number of applications. So, let us have a review of what different types of applications it is applicable to. So, we will construct a table, field, then PV stands for primary variable, and in this equation the primary variable is u. Then we have material constant, which is k. Then we have source variable, which is f, and then we have secondary variable, which could be either q or del u over del x or del u over del y. So, again remember u is not displacement, it is some generalized scalar variable. It could have lot of definitions, but it certainly does not have a direction, it is a scalar. And the same thing is true for f. F is not force, f is some function, it is again a scalar variable. So, the first thing where we can apply this is in the area of heat transfer. So, if I am trying to solve a two-dimensional heat transfer problem, then the primary variable is temperature. Okay. So, the governing equation for two-dimensional heat transfer is this equation. So, temperature, a lot of times we express temperature as T, so U becomes T. Then material constant is conductivity. Then we have heat source, and finally we have, oh sorry, this shouldn't be here. So, heat and the secondary variables could be Q or del U over del X, which is the gradient of temperature in X direction, and del U over del Y, which is the gradient in Y direction. Another, so this is from heat transfer. Then if we look at mechanics, this is torsion of constant cross sectional members. What does this mean? If you have a shaft, it could be a circular shaft or a square shaft, and I am trying to do torsion on it, then it is this problem, this equation defines the solution for that. So, here what is u? U is the stress function, and we will discuss this later. So, it is a stress function, it is not stress, it is some function called a stress function, and lot of times in literature it is designated as psi. It does not have a direction, it is a scalar variable. K is equal to 1 unity, and here we use a shear modulus of shear. F equals 2 and theta equals twist per unit length. And what are the secondary variables? G theta del psi over del x is equal to minus sigma yz, and g theta del psi over del y is equal to sigma xz. So, this is thermal, this is mechanics. We will look at maybe one or two more electrostatics. So, here in electrostatics, a two-dimensional problem, this U represents scalar potential. Designated as phi. Material constant is dielectric constant. Epsilon. This is charge density. And this is displacement flux density. So, this is from electrical engineering. And then we have several others. I will just list down two, but I will not give all these details. One could be transverse deflection, of a membrane. Okay. Another could be irrotational flow. For ideal fluid. And this list is not just limited to that, we can also use it in magnetostatics and several other areas. So, the point what I am trying to make is that one single equation, Poisson's equation, if we know how to solve, we can solve a whole lot of problems, because the same finite element code can be used to solve heat transfer problem, torsion problem, electrostatics problem, deflection problem. The only thing which changes is that in one case you call U as temperature, in another case you call it a stress function, and so on and so forth. So, this gives you the overview of what the landscape is. In the next class, we will start developing some of the details of this problem. Okay. So, tomorrow we will develop, we start developing details of this problem, and this discussion will go on for at least 1 week, so that we become fairly comfortable with how to solve two-dimensional single variable problems using finite element analysis. So, thanks a lot, and we will meet tomorrow. Bye.